everyone. Thank you for joining us today. We're going to start today's webinar, Net Pay Estimation and Uncertainty Analysis with HampsonRussell. Tanya Caldwell will be our presenter today. Tanya Caldwell is CGG GeoSoftware's Product Strategy Manager for Seismic Reservoir Characterization based in our Calgary office. Tanya will be covering in this webinar a workflow for net pay estimation using the HampsonRussell products Emerge and MapPredict, as well as show uncertainty analysis techniques. The webinar will last approximately 30 minutes with questions and answers at the end of the presentation. Without further ado, I will pass off the webinar to our presenter, Tanya Caldwell.
Good morning, everybody, or good afternoon, depending upon your time zone. Welcome to this presentation. In this webinar, I will cover one of the net pay estimation techniques and uncertainty analysis using CGG's HampsonRussell software, MapPredict and Emerge. The presentation is aimed for a wider audience. It covers the subjects at the introductory level. However, if you have some technical in-depth points that you would like to be mentioned, please ask at the end of this webinar, or you can send us an email for further details. So in this talk, I will be showing you how we use multiple attribute analysis to generate volumes of porosity, V-shale, and water saturations. And later on, I will utilize those volumes for the net pay estimation using the maps. MapPredict is a map-based geophysical software, and it's formerly known as ISMap. So after the estimation, I will discuss the uncertainty analysis. So when exploring the unknown, we always want to know how much uncertainty can we tolerate. What is uncertainty analysis? Uncertainty analysis measures the propagation of error, and I will discuss on how to quantify this propagation of error, how to quantify this uncertainty with map-based geostatistics. So given a map of net pay like the one shown here, where you have drilled some wells, let's say I drilled wells A, B, C, D, E, I would like to know where is the next optimal location for us to drill. So would well F be a good well to drill? So NetPay will provide me a quantitative assessment of hydrocarbon resources. So it will provide me this answer, where is the best next location to drill, and how to not to bypass all those reserves. There are many techniques available since early 1980s to estimate net to gross pay ratio and net pay itself. For example, in 1980s, Brown and al. Introduced the first approach, of seismic attribute-based approach, an amplitude scaling approach for net pay estimation. I will talk about the approach that uses seismic attributes to estimate net pay and then to do the uncertainty analysis. And we will use this workflow using maps and HampsonRussell software. So the general workflow will be like this. I will start with seismic data, and then I go to the inversion process, and it can be either pre-stack or post-stack inversion. And with inversion, I estimate P impedance, S impedance, VPDS ratio, density if I can. After the inversion, I will predict volumes of porosity, V-shale, and water saturation. In order to predict these volumes, I also need to utilize the well data. So that's one of the requirements for this approach. In order to predict the volumes of porosity, V-shale, and water saturation, each of the wells that I'm using needs to have porosity, V-shale, and water saturation logs. And the last step will be the net pay estimation. So from the volumes, I'm going to maps and the uncertainty analysis, where I will derive some probability maps. So the approach will be done by Strata, Emerge, and MapPredict. Let's start with Emerge. So Emerge is our multiple attribute analysis program that allows you to take well log data and seismic data and combine this information and to rank the attributes. So as a result, you will derive a statistical relationship that will tell you what's the best attributes that predicts your data. So in this case, I'm starting with a porosity log, which is a red curve. S is my seismic, and P impedance, S impedance, the PVS ratio, density. And I want to rank all these attributes and see what will be the best attributes that predicts my porosity. Besides seismic, I also compute on-the-fly attributes such as average frequency, dominant frequency, different bandpass filters as well. So all these attributes go into the statistical estimation process, and we do multiple attribute regression where we derive the relationship. So in my example, the best attribute that was predicting porosity is density squared. The second best attribute is average frequency, and so on. So once I derive this relationship, I can apply it and do validation analysis. So on this plot, I am looking at two curves. The black one is my training error, number of attributes versus the training error on the y-axis. So the more attributes I add, the better my prediction gets. The red curve is the validation curve, which was computed using blind well validation test. So one by one, I excluded each well from the analysis and rerun the same training without that well, and computed this blind well validation curve, which tells me that the best number of attributes to use will be 7, because these 7 attributes give me the smallest validation error. So this helps me to derive the actual equations that I can use for the estimation of the porosity. In this example, the correlation was at 85%, the correlation between the original and the predicted logs. And then I applied the derived statistical relationship to the entire volume and predict the volume of porosity. The same iterations can be repeated on other properties, so I repeated them for V-shale and for water saturation volumes. Emerge approach is not limited to multilinear regression. We also have neural networks. And the beauty of neural networks is that they will combine numerous seismic attributes and predict higher resolution results than multilinear regression, because they take into account the non-linearity between the attributes. So with multilinear regression, the attributes are linear, the derivation is linear. For neural networks, account into non-linearity between the attributes. Once I derive the attributes, I can cut the data slices at the pay zone for the derived maps. So here I'm showing porosity average, V-shale average, and water saturation average. And this is the data set from Alberta, Canada, from Tabor-Turin field, and that's the top of the channel. So I would like to find out whether this would be a good location to drill or not for the F well, and derive the net pay estimation map from this data. So the net pay estimation will be derived using collocated co-kriging, and conditional simulation will allow us to judge the confidence levels and to do the uncertainty analysis on those net pay maps. So net pay analysis for net pay estimation in MapPredict. Here we are starting with maps. So we are done with the Emerge program. We predicted the volumes, and we are taking the maps averages around the area of interest. And we want to combine these maps and again derive the relationship to predict the net pay map. This approach also requires net pay, measured net pay values at the well locations. So I need to have input wells with net pay values in them in order to combine those input values with the map-based information and predict the final map. When I run the analysis, what we found out that porosity volume and volume of shale were giving us the best optimal net pay estimation. MapPredict also has emerge algorithm. It has kriging, co-kriging, conventional and traditional and collocated co-kriging techniques. But we start with the emerge algorithm that will combine porosity, V-shale, water saturation maps and net pay values at the well location and will predict the map. We use, again, similarly to emerge, we use multilinear regression approach, rank the attributes and derive the best relationship that predicts my net pay values at the well location. So essentially we are merging the well information with the map-based attributes. We can also utilize neural networks in this case. In my example, I did not use neural networks, I used only multilinear regression. The predicted net pay values at the well locations will not be honored exactly using this approach. There is some difference between measured and estimated approach. Ideally, I would like to exactly honor the well locations. So here I'm showing measured net pay values versus the estimated pay values, and the accuracy was again around 85–86%. So I derived this intermediate map of net pay. So this was derived using MapPredict multilinear regression approach. And then I want to improve upon this map. In order to improve upon this map, I'm going to run a geostatistical interpolation technique called collocated co-kriging. So MapPredict contains a range of geostatistical display and analysis tools such as cross-plotting, histogram, variogram analysis, well-to-well variograms, well-to-seismic variograms, and it also has standard mapping interpolation techniques incorporated, such as kriging, co-kriging, and conditional simulation techniques. So kriging and co-kriging are the standard geostatistical algorithms that we use for interpolating the data. You can plot various correlation plots, derive the maps of co-kriging area at the well location, do validation analysis on what's happening at the well location, and so on. So as a result, I come up with a better map. So this was the map derived using collocated co-kriging. And this map will actually honor the known values of the net pay at the well location. So measured and estimated values are exactly honored. And if I do blind well test, the predicted value was 73 feet of pay, while the measured value was 77 feet of pay. Next, we'll go to the uncertainty analysis. So how can I judge the error on that map? What's the uncertainty? And this is the uncertainty workflow. We created a map, one map or several maps using conventional co-kriging technique. And then we're going through sequential Gaussian simulation, SSG, to simulate different scenarios. So we perform stochastic simulation. Stochastic simulation involves creating a series of equally probable realizations of a model or a random variable. And the most popular type of simulation is called sequential Gaussian simulation. So with this SEG, we can simulate a number of possible maps, and we can make quantitative prediction about their probability of occurrence. So we can estimate the value of wells alone, so with ordinary kriging technique, or we can estimate the values of wells and plus seismic using collocated kriging. Once we are done with the simulation, we go to the analysis and we derive these maps, either probability maps or indicator maps, so we can judge the quality of the data. We can create 100 different realizations of this co-creek map in this case that shows wells and seismic, so simulation 1, simulation 50, simulation 100. From these simulations we derive probability maps. Here I'm showing the probability of net pay values between 0 and 20 feet. Next, I'm showing the probability values of finding net pay between 40 to 70 feet. And the last one will show me the higher probabilities, so that's where the net pay is higher, between 70 and 100 feet. And this is where my blind well test falls in. This is the F well. That was predicting 73 feet of net pay. And the last one, the probability of finding net pay between 100 and 200 feet will fall in this area in the northwest corner. MapPredict also uses horizontal wells. So for horizontal wells, we handle different scenarios of extraction the data. The first scenario, we can handle extraction of data between average 2 tops. We can use specific number of divisions, how we are dividing our zone of interest, or we can even use an indicator log. For example, you may use a gamma ray ratio or resistivity log to guide your extraction. Why horizontal drilling is important? Because it exposes a lot more of the reservoir rock to the wellbore surface. It is commonly used within the thin reservoirs and natural fractures and complex depositional geology. So with horizontal wells and MapPredict, you can even derive the net pay estimation more accurately. So MapPredict will allow you importing the horizontal wells, extracting the attributes on the horizontal wells, and also horizontal wells contain various engineering data or actual production values by zones. So you can utilize the horizontal wells and actually predict the production of hydrocarbon. So you can derive the map of the actual production values. Other data that can be utilized, such as flow, temperature values, pressure values, so all are indicative of the actual production values. So in this presentation I showed you how we do net pay estimation workflow to produce maps from sparse data set. These sparse data sets, this prediction will honor the actual information at the well location. Using MapPredict, you can simulate a number of various scenarios, and you can estimate the probability of occurrence. And as a result, you will produce an estimation of the actual hydrocarbon resources. So you will determine the economic feasibility and hopefully optimize the production of your reservoir. So this concludes my presentation, and I will go to questions. Yes, the first question, can we have the PowerPoint after the meeting? Yes, absolutely, you can have the PowerPoint. We'll send it out, a copy of the PowerPoint. This data is all public. The second question is, what is the difference between conventional kriging and collocated kriging techniques. So in MapPredict, we implement two approaches to co-kriging. The first approach is conventional co-kriging techniques. The second one is collocated co-kriging technique. Conventional co-kriging technique is slower because it uses many neighboring samples when we are interpolating the data. So it can have potentially a large runtime. Collocated co-kriging uses only the value that is closest to that point. That's why we mean it's actually collocated to the our final point. That's why, because it uses the closest value only, it's faster. And it also can be combined with the linear relationship assumption, which is the Markov bias assumption. And that method is very good. But for collocated co-kriging with Markov bias assumption, you need to have the seismic data at each grid location. So that's the major difference between conventional and collocated co-kriging. So for small maps, you can use conventional co-kriging. For larger ones, collocated co-kriging is efficient enough. The next question, can we provide the details on how to perform this task? Yes, we can provide the details on the algorithm, especially on multilinear regression, on absolutely. We can send you further information on it, on multilinear regression or on MapPredict. Okay, next question. Does MapPredict come up with a HampsonRussell license? Yes, MapPredict product is a HampsonRussell product. It is a part of HampsonRussell licenses. So we have GeoView license, log license, seismic license as a standard package, and then other add-ons you can buy as Strata, AVO, Emerge, and then MapPredict is another one of them. Okay, a bit more scientific question here. How about tuning effect? Will this approach take into account the tuning effect? So tuning effect is caused by the interference of waves that are closely spaced, that are happening from the closely spaced events or closely spaced reflections. So the seismic amplitude of the reflections, in case of when tuning effect happens, is affected by, the seismic amplitude is affected by the thickness variation. So when we have the tuning effect, it can affect the polarity of our strong reflections. So as a result of the tuning, for thin beds, we will have exceptionally strong reflections. So certain attributes are very sensitive to the tuning, and if these attributes will be used in multilinear regressions, they will account for the fact that we are actually using, that we have a tuning effect happening. Historically, I think Colony used the map-based amplitude scaling technique to account for the tuning effect. So you can do the amplitude scaling first on your seismic data prior to feeding that data into Emerge. He also used band-limited impedance through colored inversion for thin-bedded determination, so you can run band-limited inversion first and then use band-limited inversion and feed that into Emerge. So the results of that emerge. So in a sense, any multi-attribute approach will incorporate various seismic attributes. And these attributes will account for that, for the thin beds and for that stratigraphy below the tuning. Which attributes consider effect below tuning? Excellent question. There is a good article written by Tanner back in 1977 on basic seismic attributes when he introduced his Hilbert transform. He introduced attributes such as, instantaneous frequency, weighted amplitude cosine phase, and so on. And later on, these attributes in further publications by Tanner, he has a few articles that actually classify each of the attributes for the effect of the tuning. So I think he used the average frequencies, the time average frequencies, because they were sensitive to the frequency spikes for detecting the thin beds. So the difference between instantaneous frequency and the time average frequency was giving him the indicator of the tuning. And then there was also instantaneous phase, because that instantaneous phase was affecting the change below the tuning. Okay, there are lots of other questions. Does the water saturation have effect in generating the net pay maps? Yes, the water saturation might have the effect in generating the net pay maps. However, in this case, it was not ranked as one of the top attributes. Correct. We only used porosity in VShale. So one of the questions was, how does the water saturation affects the map? So in this case, correct, we only ended up using porosity in VShale because water saturation was not ranked as a top attribute. Okay, when we determine the number of seismic attributes, did you consider the scale difference between logs and seismic? Absolutely excellent question. So logs and seismic come up at a different scale, at a different resolution. So we upscale the log data to the seismic resolution, and then in order to account into the sampling difference between the log and the seismic data, our multilinear regression has an option to use the convolution operator. So we use the convolution operator, which will take a few neighboring log samples, so let's say 2 samples up from the logs and 2 samples down from the log, and we'll be able to predict one value from this convolution operator. Another way to account for the frequency differences, you can filter the input logs to your seismic frequencies. And of course, neural networks will account for the differences between log and seismic resolution, so they will predict higher resolution data. So the tuning effect are mitigated by emerge, so they really don't have to enter into the MapPredict calculation. Correct. When we are taking into account tuning, that will be done at the emerge stage for sure. So some people joined late and they see only the conclusion slide. We will send you a copy of this presentation, and you're welcome also to contact CGG for further details. I will just send an email to tanya.colwell@cgg.com. So if you're entering late and are still interested in hearing the presentation, I'll be happy to talk to you in person. So there are lots of other questions, very general. Can we have a copy of the presentation? Yes, you can have a copy of the presentation. The next question, why make the net pay estimate in maps and not directly in emerge as in volume? Because usually when we estimate net pay, we can estimate the net pay accurately for specific zones. We do not estimate net pay logs for the entire logging interval. If you are able to come up with the net pay log accurately, but if your geologist, petrophysicist is able to derive those logs, then yes, you can come up with a net pay volume, that would be great. But usually the estimation is limited to the map, to the specific zone. That's why we go with the map approach. Okay, so this concludes my presentation. If I did not answer your questions, we will send the answer to your questions after the presentation. Thank you very much for attending it.
Thank you for attending the CGG GeoSoftware webinar on net pay estimation and uncertainty analysis using HampsonRussell software. If we were not able to answer your questions today, we will follow up with you after the webinar. If you have any additional questions come up, please send us an email at gs.insights@cgg.com. We will send out a copy of the presentation as well as a copy of the recording of today's webinar. To learn more about HampsonRussell's Emerge and MapPredict products, as well as the entire GeoSoftware portfolio, visit our website at cgg.com. We appreciate your interest and thank you for joining today's webinar.